A warm welcome to electronic circuits. In this video we will understand what is load line and cue point. So what is an electronic circuit? An electronic circuit will normally consist of both active and passive components arranged in such a way that passive components will control the active component and act as a signal path. So if you consider this is the input, this is your output. So there is a path between input and output, and if you take the gain of the amplifier, it has been nothing but resistance connected at collector by resistance connected at emitter. So if you consider this circuit, it is nothing but RC which is being connected at the emitter, and RE is nothing but the resistance connected at the emitter. So RC by RE will decide the gain of the amplifier, and this 1 by GM will have less influence on the gain. So approximate gain equation is minus RC by RE. So this is what is the meaning of electronic circuits. Then what is amplifier? So amplifier is nothing but a circuit which magnifies an input signal and produces output signal whose magnitude is larger and directly proportional to the input. So suppose if you give this is your input to the amplifier, and the gain of the amplifier is, suppose it is going to be 10, and you are going to supply a voltage of 20 volts to the circuit DC, right? This is your AC and this is your DC. Suppose if this is 0.5 and it is minus 0.5. So peak to peak voltage of 1 volts is being supplied as the input to the amplifier, and what will be the output? If it is properly biased, the output will be 10 times. So one is V naught is 10 times V in, so V naught is 10 volts. So this will be plus 5 and this extreme is minus 5. This is the explanation for amplifier. So it magnifies the input and gives the output as it is, or the input characteristics of the signal is not changed at the output, only the amplitude of the signal will be changed. The frequency content of the signal will not be changed. That is what is the meaning, and this is being achieved only when you operate the transistor which is being present in the circuit in active region in the case of BJT, and if you take MOSFET as the active element, then it should be biased in saturation, and this is done by a circuit called as biasing circuit. So if you want to analyze amplifiers, you have to use superposition theorem. Superposition theorem is applicable only when the circuit is linear. So somehow you will have to make the circuit linear. So what we do is we bias the circuit so that the circuit is going to behave linearly. Then we have to do DC analysis separately and AC analysis separately. DC analysis in the sense, when you do DC analysis or DC response, the AC supply to the circuit should be made equal to 0. So amplifier will contain both AC and DC. So what we should do is we should consider only one source at a time. So if you consider DC source, AC source should be made equal to 0 and DC should be applied, and you should take the response. For the other time, if you have to apply AC and make DC source as 0, and you will have to consider the response, and you will have to add both the responses together. So if it is small I, small v, then you are going to work with AC signal. If it is capital I, capital B, then it is nothing but DC signal. And if it is small I and capital B, then it is instantaneous value. So superposition theorem is nothing but we want to do DC analysis and AC analysis. So when you do DC analysis, the capacitors are considered to be open circuit. Circuit will contain DC sources and it is called DC equivalent circuit. So if you consider this circuit, it will have capacitors to be considered as 0. So why? Because Xc is 1 by 2 pi f into C. So f is equal to 0. So reactance of the capacitor becomes infinity, which is nothing but open circuit. The second point says it should contain only DC. So DC sources should be present. Then the transistor or the capacitor should be considered as open. So if it is made open, then Vs will not be connected to the circuit, so it doesn't have any effect. So you can neglect that. So this is R1, this is R2, RC, and this is RE. Okay, then selecting proper supply voltage is VCC. Resistance, which are nothing but R1, R2, RC and RE, which will fix the Q point of the amplifier. And Q point particularly, if you take this IC, this is IC versus VCE, this line is drawn on the output characteristics of the transistor, and normally what we do is we bias in the, we fix the Q point in the middle of this line is called load line. So this is ICQ and VCEQ, and this is called Q point. And this Q point is also called as large signal parameter. Why? Because the signal level involved will be much larger, so it is called as large signal parameter. And this will end up end up being with DC values. When you go for AC analysis, the capacitance again 1 by 2 pi FC reactance of the capacitor. The F is larger, so the reactance of the capacitor will be smaller, so it should be considered as short circuit. The circuit will contain AC sources. That means DC sources are equal to 0. Then replace the transistor by its small signal equivalent model. So equivalent model is nothing but model is a combination of circuit element properly chosen that best approximate the actual behavior of the circuit device under specific operating conditions. Specific operating condition says the transistor should be biased in active region. Why? Because in that region the circuit is going to behave linearly. So if you consider the transistor, this is the transistor, base emitter, collector emitter. So base emitter should be forward bias and collector to base junction should be reverse bias. So that is called as biasing. So this is considered, and we have to replace between base and emitter there is a diffusion resistance which is R pi. Between collector and emitter there is a current which is beta times IB, and between collector and emitter you have a resistor R0. So this R0 is considered. Why? Because it will have early effect. So to consider the early effect in the model, you have to consider R0. So this should be considered, or this should be taken. So if you consider this DC should be made equal to 0. So if that is the case, and R1 and R2 will appear to be in parallel. So this is my VI. The capacitor should be considered as short circuit. Then I have R1 R1, R2. Again this is my base terminal. So between base and emitter I have what is called as R pi. Between collector and emitter I have a current source which is GMB5, and then between emitter and ground I have a resistor which is RE. I am going to neglect R0. Why? Because R0 is VA by ICQ. VA is yearly voltage. If I consider yearly voltage as infinity, R0 will become infinity. So it can be considered as open circuit. And then I will consider RC, where the RC other end is being grounded. So this is called small signal equivalent. So DC analysis you will get DC quantities. AC analysis you will have to follow this procedure. And when we consider AC analysis, the resistance at these load line will have slope. The slope depends upon the resistance at load. So when you consider this circuit, the load resistance will be R0, or you consider RL as purely which is equal to RC, AC load resistance. When you consider DC load resistance is nothing but again it is going to be we have to do DC analysis and we will obtain it. In the coming slides we will see how to calculate the load resistances. So what is biasing? Biasing is done by using external components such as resistor, capacitors and DC voltages to establish proper collector current and collector to emitter voltage across the transistor. And this is being done to amplify input signal linearly and without any distortion. And condition for biasing is the base emitter voltage should be forward bias. So we apply 0.7 volts for the silicon transistor, and collector to base junction should be reverse bias. And if you consider that the collector to emitter voltage should be greater than saturation voltage of the transistor. Modes of operation. If you consider the modes of operation, this has been base to emitter junction has been forward bias. So if you consider on the last side we have considered it should be 0.7, and collector to base junction should be reverse bias. So it will be operated in forward active mode. So this is the desired mode of operation. If you consider to this extreme, when base emitter voltage is negative, the transistor is reverse biased or the entirely reversed. Base to collector junction is also forward bias. So it is forward bias. Base to collector junction is forward bias, and base to emitter voltage is also reverse bias. So it is called inverse active region, and it is not desired to be operated. Transistor should not be desired to be operated in this region. So what is the operating point? Operating point is the DC collector current and collector emitter voltage when no input AC input is applied, or collectively referred to as operating point. The operating point, so this is considered to be, suppose this is considered to be my operating point. So IC is beta times IB plus 1 plus beta into IC. So when temperature is being increased, the first parameter which will change is reverse saturation current, and then beta will change with respect to one transistor to other, as well as when temperature is going to change, this beta is also going to change, and VBE is also going to change. So this ICO double up for every 10 degree rise in temperature. Beta again with respect to temperature it is going to change, or when you change the transistor, beta is going to vary. The next thing is base emitter voltage. It is going to decrease by 2 millivolts for every degree rise in temperature. So this is the so the Q point can shift this side near the saturation or near cutoff region. So it would shift upwards or downwards. This is the reason we should select the biasing circuit properly. So judicious selection of operating point is important for faithful amplification of input signal. So the proper way of choosing is Q point should be in the middle. So if it is selected in the middle, both positive off cycle and the negative off cycle is reproduced faithfully at the output. If you select the Q point near the cutoff region, the positive off is being clipped off at the output, and this is going to cause distortion. And if you consider the Q point to be selected near saturation, when you consider the voltage waveform output, the negative off is being clipped off and it is going to cause distortion. So the proper way is you should select Q point in the middle of the load line. Why? Because if you consider this, we are biasing the transistor in which region? Active region. In active region, where current is constant. We don't want IC to change. That is what is required when you do with biasing. Coming to the load line, it's a graphical way of analyzing a circuit, and an actual line is drawn on the characteristic curve of the device. The slope, if you consider this as load line, in the first slide we have seen fixed bias circuit. So this is what is the circuit we have assumed. So when you apply KVL at the collector to emitter loop, you will have minus VCC plus IC into RC plus VCE is equal to 0. So this VCE is equal to VCC minus IC into RC. So when IC is equal to 0, VCE is equal to VCC, and when VCE is equal to 0, IC is VCC by RC. So this line is called DC load line. This extreme limit is VCC, which is equal to RC, and this point is, you know that this is equal to when collector current is equal to 0. So if you consider this, the slope of the line depends upon load. The slope of the line which depends upon the load, and why it is called DC load line? The circuit is purely consisting of only DC. That's why it is called DC load line. And dynamic load line or AC load line is, since capacitors are considered, when you assume AC analysis, the capacitor is considered to be short circuited, and the effective resistance is whatever which is being connected at the output. So if you consider that for the AC analysis, you will have RC and RL. So R dash L is equal to RC parallel RL. Why? Because we are considering AC analysis. So RC parallel RL. That is what is the load resistance. And thank you for your attention. Thank you.